In this lesson, we're going to be looking at how abstract data types like linked lists can be set up and used. You have to be familiar with both the pseudocode form, and later on, you will need to be familiar with the programming language equivalent of it. We're going to be looking at Python in a later series of lessons. Another focus of this lesson would be to review other abstract data types, especially those from AS level like stacks and queues. Now in year 12, you just needed to know about what stacks and queues were and how they operated. For year 13, you would need to know how to implement those using pseudocode. And this could be asked both in paper 3 in the form of pseudocode or paper 4 in the form of actual code. So before we begin, let's do a prior knowledge check. Do you know what an abstract data type is? What are the common operations that can be performed on an ADT? How do you implement a stack? How do you implement a queue? And perhaps some of you might know this, how do you implement a linked list? If you can answer all of these questions, then you're going to find this particular lesson a lot more easier to handle. If not, then my suggestion is perhaps go and visit the year 12 lesson first. We will do a basic cursory overview of stacks, queues, and linked lists before we continue on with the actual pseudocode for linked lists. So let's start with our basic structure, which is a 1D array. This is a non-composite data type. It uses an index. It has a lower bound, which is the first element, and an upper bound, which is the last element. Now on screen, you can see the basic pseudocode equivalent of setting up an array and assigning a value to one element of that array. Pretty straightforward. Another type of data structure is a 2D array. Now this one again is a non-composite data type. You can probably think of it more like a table. It uses a row index and a column index. Lower bound is the first element and upper bound is the last element. But in this particular case, you're going to have two elements or two dimensions in that array bracket. The first one is the row and the second one is the column. Now, when you want to assign a value to a 2D array, you would need to assign it by specifying both the row position and the column position. So my array 7, 0 means you look at the 7th row, and then you look at the column which is index 0, which is basically the first column, and that's where you store 16. Now those two are the most common types of data structures. However, sometimes we need to create a data structure where we can actually apply some methods or processes to. These are known as abstract data types. And one of the most common ones is a stack, because stack not only allows you to store data in it, it also allows you to apply methods to it. For example, you can push an item into the stack, you can pop an item out of the stack, whereas with an array, you just store things in it. Now, the combination of the storage and the methods is what makes it an abstract data type. And the stack basically operates on the last in, first out principle. So the last item that's pushed into the stack is the first one to pop out. On screen, you can see an implementation of the stack where you've got an array and two pointers. The base pointer is always going to be at position 1. The top pointer is the one that you manipulate. So when you want to push an item in, the top pointer goes +1. When you want to remove an item, the top pointer goes -1. Now we never remove data out of that array. The data always stays in. It's not like we delete that data because that would require an extra file operation. We just simply update the addresses. So the data might still be there. You just move the pointer and say, well, okay, the top pointer is now moved downwards. That means we popped a value out. And if somebody wants to push a value in now, it will overwrite the previous value when we do +1 to move the top pointer back up again. A queue is just like a stack. It's again an abstract data type. In this case, we've got that array structure and we've got two pointers again, the front pointer and the end pointer. Now a queue operates in the first in, first out principle. So the first value coming in is the first one to be removed. And these processes or methods are called enqueue and dequeue. So in this particular case, 27 will be the first item to be removed. So the front pointer is moved +1. It moves to 34. And if you want to add a new value, we just simply add a value in index 5 and move the end pointer to that particular position. So end pointer +1. Now queues have a problem that when you reach the end of the list, like the end pointer reaches 7, the queue is full. So we can probably create a circular queue that follows the front pointer. So when you reach 7 and there's space at the top, because we just dequeued 27, we'll reset the end pointer to index position 1 and you will end up creating a circular queue. Now on screen, you will see some stack operations in pseudocode. How do you set up a stack? Well, you set up an array in this case of 10 values of integer type. We then declare our top and base pointers. We have a stack full, which is a variable that contains the length of that particular stack. The push operation just compares the top pointer to stack full. Well, if the top pointer, which begins with 0, is less than 10, then top pointer is top pointer plus 1, so you increment it, and in that particular position you store the item. If it's not less than 10, for example, if it is 10, then that means that the stack is full, so that's your else branch of the if statement. To remove an item, the pop operation will do another comparison. In this case, we'll compare the top pointer and check if it's equivalent to the base pointer minus 1. So that basically means it hasn't reached 0. 1 minus 1 is 0. If that's the case, then we output the stack is empty, because if the top pointer has reached 0, that basically means there's no items in the list that you can pop. Otherwise, the item that we're popping out is the one stored at that top pointer, and then we decrement the top pointer because you've got to keep reducing it. Remember, we don't work with the base pointer whatsoever in a stack. It's only the top pointer that's either incremented or decremented. So do pause the video and have a look at the pseudocode. Now on screen you'll see a bit of Python code that will help you create a stack and the relevant operations. So you might want to pause the video and experiment with this code to see if you can implement a stack. And when you're ready, continue. So that was all about stacks. The next abstract data type that we need to handle is a queue. A queue uses a front pointer and a rear pointer, and in this case we manipulate both of them. So when we're trying to dequeue 27, the front pointer goes to index 2, so that's front pointer is equal to front pointer plus 1. When we want to add an item, for example, we want to enqueue31, the rear pointer is also incremented, so you end up with rear pointer equals rear pointer plus 1. Now we already talked about what could happen if the rear pointer reaches 10 and you're dequeuing a lot of items and you end up with the front pointer at 9. That means 8 spaces are free. In this particular case, you could set up a circular queue where you could probably put a selection in that if the rear pointer is at 10 and the front pointer is not at 1, then you can set rear pointer to 1, and that way you follow the front pointer as it goes along. And perhaps you could do the same thing for the front pointer, that if the front pointer is at 10 and the rear pointer is not at 1, then the front pointer could be reset back to 1 as well. On screen you can see some circular queue operations. The queue length is 4, the front pointer is at 10 and the rear pointer is at 3. So when we dequeue 23, the front pointer is reset to position 1 because that's now free and the rear pointer isn't at that particular place. Now on screen you will see the relevant pseudocode for the different operations for a queue. To set up a queue, we do exactly what we did for a stack. We set up an array, in this case of 10 values of integer type. We set up the front and rear pointer. We set up the variables queue length and queue full, and then we assign values to those. So queue length is the number of items in a queue, and queue full would be perhaps 10 because that's when the queue is full. We then set up the pseudocode for the two processes enqueue and dequeue, and that involves comparing the queue length with queue full. If the queue length is equal to queue full, then basically we need to output queue is full. Otherwise, we then check the rear pointer and then we increment it accordingly and insert items in the correct place. To dequeue, we check if the queue length is 0. If it is, then we output the message the queue is empty because obviously there's nothing in the queue. Otherwise, we then update the front pointer, and the queue length is also decremented because you just removed an item from the queue. So do pause the video and try to understand the pseudocode. It should be pretty straightforward. You will be asked to write about this in paper 3 and code this in paper 4. Now on screen you see examples of Python code which could be used to set up a queue. Remember, there's lots of different versions of pseudocode. You can write it a number of different ways. However, if you understand the logic, chances are that your code will always work, and similarly your pseudocode will get you full mark. So do pause the video and try to implement this, and when you're ready, continue. Okay, so you've just revisited the structures that we looked at AS level, and the final structure that we just focused on at AS was linked list. Now, linked lists can be used to create queues or stacks as well as graphs and binary trees. They're also very useful for much more complex tasks such as the lifecycle management for an operating system application, the browser's navigation buttons which allow you to navigate between different websites, and so on. Quite a lot of complex functionality is possible through the use of linked lists. A linked list in its very simplest form is two pieces of items together, the data and a pointer that points to the next item in the list. That's all it is. Collectively, these two are known as a node. Now, when we start a linked list, we have something called the head, which is the first item of the linked list. This points to the second, then the third, and the fourth, and so on, until you reach the last item, which points to nothing. It uses a pointer that's known as the null pointer. Normally, we associate -1 as the null pointer. Now, the linked list could be sorted or it could be unsorted. That depends on what you want to use it for. And the way you manipulate pointers can result in the linked list acting as a stack or a queue or something completely different. Now, in all of these structures, pointers are essential. Stacks, queues, and linked lists all use them. For a stack, there are two pointers, a base pointer on top of the stack pointer, and when they're equal, that basically means there's only one item left in the stack. A queue also has two pointers, a front pointer and a rear pointer, and when they're equal, that means there's only one item in the queue. Linked list, on the other hand, has a start pointer and a free pointer. But for every data item or element that's in the linked list, there's also a pointer attached to it. So if you've got 10 items, then you've got 10 pointers plus the two that you're using at the start of the list pointer and a free pointer. Now, if the free pointer gets to -1, that basically means the linked list is full. Each data item and its pointer is collectively known as a node. So what is a pointer exactly? Well, a pointer is simply a memory location or an address. That's all it is. We just point to the index in another array or another memory location. That's all a pointer is. Okay, go over there, fetch that data, or the next data item from here is there. So they just basically give you directions to navigate the structure that you've set up in memory. Now let's focus on linked lists in a bit more detail because this is the major abstract data type that we need to study for at A2 level. And the linked list can be utilized as a stack or a queue as well. And in a stack, the start pointer is seen as top of the stack pointer and the data item is only added to the start of the linked list and a node is only removed from the start of the linked list. A queue can also be implemented from a linked list. The start pointer is seen as the front of the queue and data items are always added to the end of the linked list and items are always removed from the start of the linked list. So you manipulate the start pointer, you make sure that if you're removing something, the start pointer moves to the next possible index, and similarly if you want to add an item, you increment the free pointer or the heap start pointer, whatever you call it, the rear pointer basically, to make sure that the item is added at that particular point. So stacks and queues are basically special variations of a linked list which you can manipulate the pointers to suit the kind of behavior you want a linked list to demonstrate. But how do we go about setting up the linked list? Now on screen you see a possible pseudocode. There are multiple variants of this. This one in particular uses a set of two arrays, the start pointer, the heap pointer as variables, the index as a variable. We then initialize those pointers and then we use a loop to populate the pointer values, and then finally the 11th index we set it to -1, indicating the end of the linked list. Now this is one variant of doing it. This is not the most efficient way of doing it, but it probably is the most simplest way of doing it. We can also set it up as a record type or a class or an object, and on screen you see another variant of a linked list pseudocode, but this is called the node version. This is the much more efficient way of creating a linked list. So here we define a null pointer as -1 because we don't want to keep calling it -1 all the way through the code. Later on, if you want to change the null pointer to something else, we can do that instead of changing every instance of -1 to a new value. So next up, we define our record type list node. In here, we've got the data, which is a string data. We're going to use that. We could change it to integer if we so wish. And we're going to also have a pointer which points to the next item perhaps. We end type, we then declare the start pointer, the free list pointers, and then we declare an array of the list node that we just created, and in this case there are 7 items in this particular array. We can use this array to now store data items and pointers, and the pointers will be associated with that particular data item. Next, we set up a procedure. In this case, we are going to call it initialize list because we want to initialize that array we've just set up, and we set the start pointer to the null pointer because there's no item in the list at the moment. We set the free list pointer to 0 because that is the next available space in the array for us to insert a new value. We then create a count control loop, for example a for loop, and we use that loop to just populate the pointer value to 1, 2, 3, 4, 5, and 6. The reason we have to only do that and we're not going from 0 to 6 is because we don't want to insert 7 because there's no index 7 in our array. So we just want to go up to index 6. So from index 0, we will say the next item is index 1, then index 2, then 3, 4, 5, and index 6. That means the index position 6 will not have a pointer pointing to index position 7, which doesn't exist. So in index position 6, we set that one to the null pointer, which is -1, and that indicates the end of the list. That's the reason why you need list index.pointer is assigned the value index +1 and not index, because you start with 0. When the index is 0, then you set the pointer position to 1. When the index is 1, you set the pointer position to 2, and so on. Now this is probably how it would look like in the computer's memory. So you've got the list array which has a data column and a pointer column, and you've got the start pointer variable location and the free list pointer variable location. And in the pointers, we are now going to populate it with 1, 2, 3, 4, 5, 6, and -1. Now how do we go about inserting values into the data column? For that, you will need to write a new bit of code, and we're going to stick with the more efficient node mechanism rather than the array mechanism. So in this case, we will need to create a new procedure. In this case, we call it insert node, and the parameter we're going to pass to it is the data item that we want to add to our linked list, and that's called new item. So if the free list pointer is not equal to the null pointer, basically that indicates there is space in the array, because if the free list pointer is equal to the null pointer, then that means that there is no space available in that linked list. So we check that condition first, and then if it's not the null pointer, then we say, well, okay, the new node pointer is now going to be the free list pointer because that's the place where we're going to insert the value. And in that pointer, in the data part, we insert the new item. So if the free list pointer was 0, then the new node pointer becomes 0, and the list 0.data contains the new item. Now we could just simplify this and simply use free list pointer there, that's fine as well, but it's much more efficient for us to create new variables so we don't end up being confused and end up altering the value of the free list pointer later on. So now we're going to say, well, okay, the free list pointer is now going to be assigned a value which is stored in the same position in the pointer table. Now, if you remember what we did when we were setting it up, we said that at index 0, the pointer is going to be 1. So the free list pointer is now going to be given the value 1 because we've just inserted a value at index position 0. So we incremented the pointer. Now we could have done it another way. We could have just simply said free list pointer is equal to free list pointer plus 1. There are lots of different ways to go around it. But this particular mechanism allows us to leverage the pointers that are already stored in the pointers part and allows us to create sorted lists. So how do we go about doing that? Well, we need to find that insertion point where we can insert, and to do that, we manipulate pointers again. So we're going to start with setting up a new pointer. In this case, we call it this node pointer, and we give it the value of the start pointer, which means start at the beginning of the list. Then the previous node pointer is given the value of the null pointer because before the start there shouldn't be anything, so that should be null or -1. We then do a check. We check if this node pointer is not the null pointer, because if this node pointer is the null pointer, that means you're at the beginning of the list and you don't really need to kind of check. And we also need to check if in the list at this node pointer, the data item is less than the new item, or greater than if you're going in the opposite direction for sorting. That allows you to then check, well, we're not at the first position. If we are not at the first position, then is the data item less than what's already stored in the current node? We then say, well, okay, remember this current node, and this node is going to now become the previous node. And in this particular node's pointer, we're going to put the pointer value that's stored at that particular location, because that allows us to point to the next node. We then compare the previous node pointer to the start pointer, and if they're equal, then we update the pointer to the start pointer, and we set the start pointer to the new node pointer. Otherwise, we insert the new node between the previous node and this node, and you can follow the logic of the pointers there. With a linked list pseudocode, you need to take your time and you need to trace out what's happening with an empty linked list. So create these pointer variables, start with the various index positions, and see if you can trace this pseudocode out. That will give you a better understanding than either listening to me or just reading the pseudocode. But once you understand how it works, you're never going to forget it, and that will make life so much easier in the exam. So pause the video, set up a trace table, put all the variables as headings, and start with index position 0. Just put in a value of your own choice, and then try to see what happens when you follow the pseudocode. Once you're finished with this, continue. Now on screen, you've got a data structure with 3 inserts. The start pointer was set at index 0 because B is the smallest value. That points out to index 1, which is the next value, which is D, and then that points to index 2, which is the third highest value, which is L, and that points to -1 because that's the end of our linked list. Now, of course, you can probably see another -1 further down that we had set up when we initialized the pointers. That's okay. The linked list will go to the first -1, and when it encounters the first -1, it just stops there. Okay, that was just inserting items into a linked list. What about finding an item in a linked list? For that, we need to define a function, which in this case is called findNode, and we're going to use the data item variable, which stores the value that we want to look for. And in this case, it returns an integer, which is the pointer that value is stored at. If, for example, the value is not in the list, we will return -1, which is the null pointer, to indicate that it doesn't exist in the list. Now, obviously, you could probably enhance it by actually putting text strings and return strings back. That's all up to you. We're just going to stick with the basic logic. We start with the current node pointer, and we set this current node pointer to the start pointer because we want to start at the beginning of the list. We now need to check the linked list till the end and compare each data item to the item we're searching for to identify either a match or return -1. So we're going to do it a bit more cleverly. We're going to use a double-barreled while loop, and in this case we're simply going to keep checking the pointers and the data items until we reach the end of the list. So we say if the current node pointer is not equal to the null pointer, because if it is equal, you're at the end of the list, and return -1, and the data that's been stored at the current node pointer is not equal to the data you're looking for, because you want to keep checking the remainder of the list if it's not there. And while it meets those two not conditions, update the current node pointer to the next pointer. So you check the next item the next time the loop comes around. So what's basically happening is that you start with the start pointer, you compare the data in index 0, and if it matches, brilliant, return index 0. Otherwise, update it to the next index, which probably will be index 1 in our case, and then compare that. And if it matches, return index 1, else go on to the next one, which is index 2, and so on, all the way down until you hit -1. And if you hit -1, which is null pointer, you exit the while loop and you return -1. Otherwise, you return whatever value you exited the loop on. So when the data item is matched, you exit the loop and you return that pointer, else you will end up till -1 and you return that. So it's a very nice and clever way to search for an item. So once again, do pause the video, do trace it out, do take your time with it, and when you're ready, continue. Another operation that you could do on a linked list is to delete a particular data item that's stored in a linked list. Now in this particular case, we're going to set up a procedure called delete node, and the data item is going to be the parameter we pass to it. We're going to start again by setting the this node pointer to the start pointer, because we're going to start at the beginning of the list to check whether the item is in there. And we once again use the same loop that we did previously, because it's exactly the same process of checking. So this node pointer is not equal to null pointer, and the list this node pointer dot data is not the same as the data item. Keep checking. Now we're going to remember the current node that we're on, and we're going to set a new pointer called previous node pointer, and we're going to assign that the value of this node pointer, because we want to remember the current node. And for the this node pointer, we're going to give that the value of the next node pointer. So we just simply point to list this node pointer dot pointer. So let's just say you're starting with the first position in index 0. The previous node pointer becomes index 0, and this node pointer becomes whatever the pointer is stored in the pointer column of index 0. So probably pointer 1. And it's going to keep doing this because it's just going to keep going. So it remembers what the previous pointer was and what the next pointer is. We then use a selection to once again check if this node pointer is not the null pointer. That basically implies that it exists. If it is the null pointer, then we will need to do something else. But if this node pointer is not the null pointer, then therefore the node exists in the list. And then we check if this node pointer is equal to the start pointer. That basically means that the first node needs to be deleted. So we move the start pointer to the next node in the list, and we simply do not delete any values, we just update the pointer. So if this node pointer ends up being index 0, then the start pointer is moved to index 1, because in index 0, in the pointer column, it's probably pointing out to index 1. Now, if that's not the case, for example, this node pointer equals the null pointer, then we make the previous node's pointer point to the current node's next pointer, thereby removing all references to the current pointer from the list. And that's basically just swapping pointer locations. As with the previous pseudocode, do pause the video, do go through this, do try to trace it out so you get a better understanding of how the pointers work and how we simply update pointer locations. We do not delete any values from the data table, because you can end up overwriting those values, which is how computers normally work. We don't simply delete a file, we just change the pointer. So we know that that location is available for writing, and the next time you want to add a value, it will overwrite that. What's the point of deleting it and just creating an empty space? And perhaps that's the reason why digital forensics can actually find things on your hard drive that you perhaps have deleted. And even if you empty your recycle bin or trash can, people can still find out what was stored on your hard drive, because the data still exists. It's just the pointers that are used to identify where the data is are updated or removed. Now finally, on screen you'll see a bit of pseudocode which is used for accessing all the nodes in a linked list. In this particular case, we create a procedure which is called output all nodes. We once again start at the beginning, so the current node pointer is set to the start pointer. We create a loop structure which allows us to go through every node of the linked list until it reaches the null pointer, which is -1. So while current node pointer is not a null pointer, output the data at the current node pointer, and then update the current node pointer to the next item or the next index that is in the pointer part of the node. And we keep looping this and outputting that. So this is again pretty straightforward. It's all well and good looking at pseudocode, but we also need to learn about implementing linked lists using Python. Your task is to implement a linked list structure using Python of your own choice. You could go the array route, you can go the record route, you can go the class object route. I'll leave that up to you. Users should be able to insert, delete, or view the list. And of course, there are short ways. You can import deque from collections library, and deque allows you to just use the built-in functions to add items, remove items, or append items in a linked list. So if you want to investigate that, you could do that. That's an even quicker way of doing things in Python. but my suggestion would be to learn how to code these functions and procedures yourself. So that's all for today's session. Hopefully you know how linked lists work, you revisited how stacks and queues are implemented and how you could use linked lists to implement them, and you perhaps have a better understanding of the use of pointers in abstract data types. That's all for today. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.